All right, let us start. Let others join at their own time. Um, so this is you can hear me, right?
Yes, sir.
Okay. So this lecture actually completes the syllabus of the course. Although this is the penultimate lecture, since we synchronized ourselves with the assignment weeks. So mm, this week we'll be talking about uh, closed loop control, mostly that of DC-DC converters, and there is to some extent a discussion on single phase inverter. Okay, so regarding closed loop control, uh, what are things are discussed are that uh, current control, and one way of current control, that is slope compensation. Current control was discussed first in the lectures, and then one instability problem of current control was discussed. Then, to avoid that instability or to get rid of that instability, this slope compensation method is used, that was discussed in the lecture. And sinusoid pulse width modulation technique, as used in single phase inverter, was discussed. Okay, although the voltage relation was not discussed in the lectures, only the process was discussed. Maybe if we have time we'll discuss, or this week or next week maybe we'll discuss. Okay, so if you have any doubt, please ask, otherwise we have a bit more questions today. Yeah, doubts? No doubts? Okay, so let me talk about one more mm, way of current control, which is not only used in DC-DC converter, but used very popularly in many other controls also. Specifically, I would say in machine control, electric machine control, this kind of current control is used, which is called hysteresis current control. It is by default stable current control. Under no circumstances this will go to the unstable zone, given that given that the current limits that you have given are within the stable zone. What I mean is, if you use this kind of current control, your current will never go beyond the band that you wish it to be in. Okay, so what is hysteresis control and why this name is given? So we know that hysteresis loop, it looks like this. So if I draw kind of a, say, linear hysteresis, it is like this, right? So suppose I am coming up here and there is a limit. So when this limit is reached, say if this is current, say when this limit is reached, this will not go beyond this set limit, whatever I max. Not necessarily you will have your uh, origin here, it can be here also. Say, I mean, the current can be completely positive also. And then when you let the current reduce, it reduces, comes here, then goes there, once again it tracks back this path. So this band is always obeyed by the current. This is called hysteresis current control. We will see one example. Suppose mm, mm, suppose you have a 10-volt DC source, okay, and say a circuit like this, okay, it like this, and you have been asked to keep the current in this inductor, this current, say at 5 ampere, okay, by controlling this switch S. Now the thing is, it is difficult to maintain a current, say current I, exactly at 5 ampere. Why so? Because the if the current shoots up a little above 5 ampere, this switch has to be opened. As soon as it reaches 5 ampere, again it has to be closed. So ideally speaking, if you want to maintain a current of exactly 5 ampere, a level current exactly of 5 ampere, then you will need ideally infinite switching frequency, right? This is true for other cases also. Suppose you are using an air conditioner to cool your room and you set it at 23 degrees centigrade. So if the air conditioner tries to keep it at 23 exactly, then although nowadays inverter ACs are different, but the olden days ACs, then it is difficult for it to keep exactly at 23. It will frequently start stop. So what is done is we create a band, okay, we create a band called the hysteresis band. So say in this case, I know that if that I have a room of tolerance of say 1 ampere total. So what I do is I create a band of 4.5 to 5.5 ampere. So total 1 ampere band I create. Okay. Now there is a current sensor here with which I sense the current. Right. Now what will happen is, as the current increases, say it was at some value, increases, as soon as it reaches 5.5 ampere, so the switch was closed, I open the switch, right? Now this is a 5 ampere, this is a 4.5 ampere. Then I let the current fall. As soon as it falls to 4.5, again I turn on the switch. Again it goes to this one. So this is hysteresis current control. So you see, I have hard bound the current. I have hard bound the current by using this mechanism. So until the controller fails, there is no way that the current will go beyond this set value of 5.5 ampere. Now if you think that for this circuit you do not have the flexibility of 1 ampere of current band, that will maybe for the specific application you cannot allow that much of current fluctuation, say you can maximum do half ampere. So what you can do is you make the band smaller, you make it maybe 5.25 ampere, and here you make it 4.75 ampere. So what will happen is our average current would still be maintained, but the peak to peak ripple will reduce. Now can you tell me what else will change in the circuit? What else will change in the circuit? So if I draw it here, maybe it now becomes something like this. Sorry. So if you see, if you want to maintain a smaller band, your switching frequency will increase, because since the band is smaller but the circuit components have not changed, so the circuit dynamics is still the same. The current is reaching the high ends and I mean the higher boundary and the lower boundary faster, so the switching frequency is much higher if you reduce the band. So what we discussed at the beginning, if you want an exact level current, ideally you will need infinite switching frequency. Now it is also possible to go for hysteresis current control for for if you want a sinusoidal current, say, sorry, say if you want a current like this, what you do is you give a band across the current. So say this one is the higher side band, sorry, lower side band, and this one is the higher side band you provide, and you keep giving the reference. So what you can do is, when you are making your controller circuit, or maybe what you can do, it you give a band value, constant band value, how much band you can tolerate, and you keep giving the reference. So your current will look like something like this. Here also the same thing. The more sinusoidal current you want, better tracking you want, you can make something like this. It will go. You can make a narrower band, but at the cost of higher switching frequency. This kind of control can also be employed in a buck converter. If you want to go for a hysteresis current control, not only buck converter, any DC-DC converter, I discussed it one day that for buck converter or boost converter, you can find out a relation between the inductor current and the output current. For buck converter, it is same, means inductor average current and output current. For boost converter, the relation comes with 1 minus d or d, whatever. So say for a buck converter, this is the inductor current IL and this is the output current IO, then average of IL is average of IO. So basically what you can do is, say if you want like this a 5 ampere current, you can simply have a band of say 5.2 ampere, 4.8 ampere. So if you do that, you will get an average 5 ampere current output at the load. So in this way you can make a constant current source. Think about it. Suppose you have employed such hysteresis current control in a buck converter. Then what you do is, mistakenly or experiment whatever, you short circuit the buck converter output. Simply short circuit. That will not damage anything. Why? Because your current is controlled. Right? There is no harm in short circuiting a current source. This is nothing but an current source. Actually, what is a current source? Current sources do not occur naturally. A current source is nothing but a variable DC voltage source in series with an inductor. That is what we have here. See, this is a variable voltage source. A voltage source which is being chopped is a variable voltage source in series with an inductor that makes a current source. Okay. All right. So this is another way of current control. A very simple way. This is very much used, as I said, in machines. Say for example, say this kind of current you can give in PMSMs or say BLDC machines. BLDC machines require this kind of current, 120-degree conduction, this kind of current they need. So these parts, you see, these flat top parts you can control by hysteresis current control. So they will look like this, they will look like. Say for example, SRM, switch reluctance motors. Switch reluctance motors, mm, maybe at base speed they draw currents like this, but beyond base speed the current tend to increase. That is very natural. If you, I mean, it's not beyond base speed, below base speed the current tends to increase like any machine. So the current tries to go like this in a SRM. So you can control that current to control the torque by, once it reaches here, you put the hysteresis current controller which chops the current like this and makes the current like this, so you can control the torque. So this is a very popular way of controlling the current in a circuit that I want to discuss. If you have no more doubt, I mean, if you have no doubt, then we will go to questions.
Sir,
Yeah.
this hysteresis current control should be in the feedback loop, is it, sir?
Yes, any kind of control is in feedback loop. So say if I take the example of this buck converter, there will be a current sensor here in series with the inductor, which will go to the controller.
So we will set the upper and lower limits in the controller.
Hmm.
When based on that, if the current IL is going beyond the
Just a minute. Could you please
set.
excuse me for a moment? Just a second.
Okay.
Just a second. Yeah, sorry, go ahead.
Sir, when this current IL
Hmm.
is going beyond the set limit, higher limit of hysteresis that we are setting,
Hmm.
then it will remain the current will this firing angle of the switch will be controlled in such a way this IL is remaining at the higher
No,
hysteresis.
no, no. Do not even think like that. You look at this circuit. If the current, say, I have the band like this. Say here in this case, you see, I had the band like this. As soon as the current reaches or just crosses the band, I simply turn off the switch. Firing angle and all, do not talk like firing angle here. We're talking about DC circuits. Okay. As soon as it
That is
crosses
not a
the
duty
upper
cycle.
limit, I turn off the switch. The current starts falling. Why does the current start falling? Because the current goes through this loop. There is a resistance in this loop, so it dissipates the energy stored in the inductor. So it starts falling like this. As soon as it goes below, just below the lower limit, I turn on the switch once again. Again, the current starts increasing like this. This way it goes.
Uh, Sir, the sinusoidal band you have given
Hmm.
at the bottom,
Hmm.
uh, how to implement this sinusoidal band?
It is the same thing. Generally, what happens is you have some controller, okay? Some controller. This controller tells you that this sinusoidal current you need to achieve whatever you want to achieve. Say you are trying to achieve certain amount of torque in a machine. Okay, so this current you need to get the torque. Okay, now what you will do is you will feed this to when say this controller is say maybe a PI or whatever. Generally PIs do not give things like this, so whatever controller it is, this thing you give to a microcontroller. Okay, now a microcontroller, apart from this sinusoid, what else value you give the value of band. Okay, and you write a code in the microcontroller. You tell the code that whatever reference you are getting, you add and subtract. Say I take, say, band equals say beta, so my reference signal is say I ref. So you write the hysteresis control loop such that your current is always between Iref plus beta by 2 to Iref minus beta by 2. Yeah, it will make sure that the current is inside this band like this. Narrower this band, as you can understand, better you can track the sinusoidal reference.
Sir, here you told this current source is represented by a variable voltage source with the impedance.
I'm not saying represented, I'm saying that current sources do not appear in nature. So if you have to make a current source is nothing but a variable voltage source. Means you have to make the current source as a variable voltage source in series with an inductor.
Okay. Sir, the characteristics of a current source is whichever potential is appearing across the current source, it will provide the same value of current. Uh,
Hmm, hmm.
that is the so how this equivalent circuit can have that characteristic.
Okay. So if you see here, if I talk about a buck converter, say, so how does it look like? It is like this. So it is a variable voltage source in series with an inductor, right? Now,
Yes.
what
Okay.
is happening? You want certain, say, I say whatever might happen, I have say 20-volt input. Whatever might happen to the load, I want a 5 ampere output, right? Now you see the maximum output that I can have is 20 volt, right? Ideally speaking, 20 volt.
Yeah.
So 4 ohm, right? So this is the maximum load that this can support within its limit.
Okay. So maximum means okay. If you switch on this way for entire time, if you switch on the switch, then it will be 20.
It will be
Ideally.
25 ampere constant.
Yeah. Okay.
You cannot have more than that. For that, you have to increase this. Now, if you remain somewhere between 0 to 4, you can always have a control on the current, 5 ampere. Again, I am saying everything in ideal conditions. In a buck converter, it's very unlikely that it will go beyond zero point 0.5, zero point 0.6 duty ratio. We discussed the parasites would stop it from having such a. Sorry, I'm saying the other way around. Very small buck ratio if you want that the parasites would stop you. The device drops and other things will become more and more prominent. Like boost, you cannot have a very high boost.
So this can be considered as a 5 amps current source.
Yes, provided you have that type of control.
Mhm.
For a boost also, you can say that. Say if you have a boost converter, can you see that a boost converter is actually a voltage, so is that actually a current sourced converter, while a buck converter is a voltage sourced converter. A boost converter is a current sourced converter.
Yeah. Yes. This it can be the source and impedance can be replaced with the current source.
Yes. So say if I replace this thing instead of this part, sorry, instead of this part, if I draw current source here, so when I open the switch, this current source supplies the load directly. When I close the switch, this current source is short circuited. So in a boost circuit actually is an the boost circuit is an example of how we realize current sources by using variable voltage source in series with inductor. Okay.
Sir, at that time we have to put this impedance in parallel.
Which impedance?
This impedance in series with the voltage source.
For the boost you are talking about?
Yes, sir.
Why do we need the impedance in parallel?
No, no. This inductance, which is in series with the voltage source,
No,
has to
we
be
do
placed
not
in parallel.
need. Why? Is the current source, constant current source.
Uh,
It's like this. So when you're say I am drawing the switching like this, so when your switch is closed, I am drawing the diode current. Okay. When the switch is closed, your diode current is nothing. Sorry, your diode current is zero.
yeah.
True.
Yes, sir.
And when it is open, your diode current is whatever source current you have here, Is that much.
Mhm.
So this is the exact diode current that you get in a what is that called, boost converter. Only thing is this is not like this. I will not draw it here. It is dropping because it has inductor, so current drops like this. If you have a very high value of inductor, you will get this kind of flat top current in the diode. Okay, anything else? Okay, then we will dive into the problems, and if you have any question in later stage, you can ask. Look at this circuit. Okay, you can see this circuit, or should I make it larger? Input voltage L, Q1, Q2, Q3, Q4, four switches are there, and from the switch notation that they have drawn in the question, it is an IGBT. IGBTs are mixtures of MOSFETs and transistors. So from the MOSFET, it takes advantage of higher frequency, switching frequency, which transistor doesn't have, while from transistor, they take the advantage of higher voltage current rating. One more advantage that IGBT takes from the MOSFET is that it is a voltage driven switch. Okay, it's difficult to control current driven switches. Now, why I am saying or telling all this, okay, let me make this diagram bigger for you. Small, I did not realize it's this small. Yeah, so Q1, Q2 is okay, they are being gated. So DC-DC converter shown below, Q1 and Q4 are given identical gate drives of duty cycle D. Q2, Q3 bases are shorted to their respective emitters as shown. Now you see what I said is that an IGBT is a voltage driven switch. What does it mean? It means that it has a capacitor here. The capacitor for IGBT, it is base collector emitter, so we can say BE. So this is the base emitter capacitor that you have to charge up to turn on the IGBT. Now you see it is shorted. So if you short it, that means you have made this IGBT in this circuit permanently turned off. This capacitor voltage is always zero. So I am talking about Q3 and Q2. The bases are shorted to the emitters. So these two IGBTs are always turned off. So only the diodes are there parallel to them. IGBTs do not have body diodes, so this must be externally connected diodes. Only the diodes are there that might be functional under certain conditions. So we will now see how the circuit might operate. So they are saying that Q1 and Q4 are given identical gate drives of duty cycle D. Okay, Q2 and Q3 are shorted. Find the input output voltage relationship. Okay, see, this is an unknown DC-DC converter. I discussed this sometimes that if you have unknown DC-DC converters, try to understand the inductor voltage waveform. Okay, voltage and current waveform. So we will try to apply that. So what is happening? What is happening when I am turning on Q1 and Q4? Okay, so Q1, Q4, they are being turned on together. So when I'm turning on Q1 and Q4, what I will draw is I will draw inductor current. So I will assume my positive inductor current direction in this way. So I will draw inductor current as well as inductor voltage. Okay. Now say I will draw another cycle. Right. Now how will inductor current look like and how will inductor voltage look like? Let us draw inductor voltage first. First I will assume because wait. So you see, this thing looks like a boost converter. Voltage source followed by an inductor followed by switches. So this looks like voltage boost converter. So we will start solving this problem assuming that V out is greater than V in. If we face a problem in between, or if you understand that that assumption is wrong, then we will do the other way around. But as far as it looks like, V out is going to be larger than V in. Okay. So why this assumption is important, we will see. So you see now Q1 and Q2 are Q1 and Q4 are closed. Now look at the current path. The current is now flowing. I will show it red. Is now flowing from DC source to switch to the load, comes back through this switch to DC source, right? So I will remove this, otherwise it will be clumsy. Now since I have taken IL in this fashion, I have to take VL also in this fashion, right? Then only I can write I equals, sorry, VL equals L DIL dt. Okay. Now when Q1 and Q4 are like this, what we can see, what is VL? Say if I talk in terms of this ground,
V in
this is V in, and what
minus of
about
minus V out.
this? What about this? This is connected
Minus V out.
minus V out. Just a minute, let me understand once more. This port is connected here, so this is shorted, so this is at ground. If this is at ground, then this is minus V out. So yes, so during this time my inductor voltage VL is V in minus minus of V out, right? So V in plus V out. Am I correct?
Yes, sir. Ambali.
This is at minus because you see it is flowing like this. Q4 is shorted, so this point becomes the ground. So this is at lower potential, minus V out, that is connected to this point of inductor. So minus V out, VL, yes. So it is positive, V in plus V out. Again, there is one more thing here. Although they have shown V out like this, we do not know the absolute magnitude of V out. but anyway, let us take it positive for now. So it is positive. So if VL is positive, my inductor current is rising. Now what is happening is we are turning off Q1 and Q2. So these things I will now remove. This is always at Vin. Oh, sorry, this was VL. Always at Vin. Now this is removed. Now what is happening is this inductor was carrying the current. Okay. So that current must continue. Just a minute. Yeah. So that current must continue. So it will go like this. Through the diode it will flow, go to the source, come back from the source, through this diode it will go back, right? So now this part is grounded because the diode is conducting. So this is plus V out, this diode is shorted, so this is plus V out. So our inductor voltage is V in minus V out. Thing is, if this is positive, this has to be negative, otherwise we will not get average zero voltage across the
Sir,
inductor. Hmm.
sir,
What?
that voltage should be V out minus V in, right? Because for the polarity reverses, so
No,
output is V naught.
no, it will not be. See, I have taken VL as this. I have taken its
Okay.
positive here, taken its negative here. So whenever I am drawing the waveform,
Mm.
that means I am measuring the voltage in this direction. So
Okay.
I have to always do the voltage here minus the voltage here.
Okay. Okay, sir.
In the middle of the problem, you cannot change the polarity. Yes, the polarity changes, but when you are drawing the waveforms, you have to have a reference. No,
Okay. Okay. Yeah, that change in polarity we are making
there is a
as
change
a
in
we are
polarity.
drawing
Look,
the
look at this waveform. You are correct. There is a change in
negative side.
polarity, but the drawing, but we can say it is negative because we have assumed these plus and minus things here.
Okay.
In the middle of the waveform, I cannot change that. That has to be held fixed throughout. So what I have is here it is V in plus V out. Here it is V in minus V out, right? So
Yes,
this is the inductor voltage and the current will drop. So this is the inductor voltage. Now inductor voltage has to be 0. Average inductor voltage has to be 0 over a complete period, and it is a steady state. So we can apply that theorem. So what we can say is on time dTs, inductor voltage is V in plus V naught, and off time 1 minus d Ts, it is V in minus V naught. This equal to 0, right? So what do we have? We have dV in plus dV naught plus V in minus V naught minus dV in plus dV naught equals 0. So this gets cancelled out, this gets cancelled out. Uh, so dV naught 2 dV naught minus V naught. So 2d minus 1 V naught equals mm, sorry, plus V in equals 0. So what we have is V out by V in equals mm, 1 minute. So V in by V naught is this. So 1 minus 1 by 2d minus 1, or 1 by 1 minus 2d. Did I do it correctly? Minus V in by V naught is this. So V naught by V in is the reciprocal of the minus sign. Yes. So you see, this thing looks like a boost converter, 1 by 1 minus 2D. And there is one catch here. Catch is, say our V in is always positive if I keep my input voltage is not changing, but the D2 ratio is in my hand. I can change D2 ratio. Now if I want a positive output voltage, I must have 1 minus 2D positive, means 2D less than 1, D less than 0.5. So basically with this polarity I will talk about. Okay, so if I say output voltage is positive, that means this is at higher potential. So if I have a duty ratio less than 0.5, I will have a positive output voltage, means this will be at higher potential, this A. And if I have duty ratio more than 0.5, it will reverse. It will reverse. In that case, what will happen is,
Sir, at
mhm,
sir, at point 5, it seems to be going to 0.
yes,
Sorry, infinity. Infinity.
yes, it tends to go to infinity. So maybe it will look something like this.
If you put 1, it becomes negative, I think. D equal to 1.
Ah, true, true. So I should draw like this, right?
Sir,
Yeah.
actually, as you said, this converter is nothing but a boost converter with two switches and two diodes.
Hmm.
But how? But the transfer function here is where, sorry, the gain V naught by V in, it seems to be varying, different.
Yes. See, it is not a boost converter. In this boost converter, you see the voltage source is followed by an inductor followed by a switch. So that kind of configuration is here also.
Mm.
So I thought that it might have a boost property, that where the output voltage will be more than input voltage. Because see, I have to draw this waveform, I have to take something larger, something higher than the other.
Yeah.
And by
Yeah, sir.
doing that,
Because
if
in
I, Mhm.
yeah, because in boost converter on time the source will not be supplying the load
Yes,
in
yes.
the boost converter. Whereas
Mm.
here it is.
Here it is always supplying the load. Say in buck converter, it happens like when you are studying buck converter for the very first time, we draw many things that say if this is the buck converter like this. Now when we start drawing the waveforms, we say that when the switch is closed, inductor voltage, say when the switch is open, the inductor voltage is negative. That is understandable because the inductor must be uh, the inductor current must be flowing through this diode, so it must be negative. Inductor voltage must be negative, inductor voltage. But when the switch is closed, then how do I know inductor voltage is positive? When the switch is closed, inductor voltage can be positive only if input voltage is greater than output voltage. But how do I know? Even before analyzing the circuit. So in that case, what we do is, Say assume that this is not true. Say this is not true. Induct output voltage is greater than input voltage. So what will happen is, when the switch is open, this during this time the inductor current will drop. Again, if this is true, in when the switch is closed, then also the current will drop. Then it will become zero. In other words, this circuit will never start at all. So our assumption that this was wrong, this was true. So in this way, I told you that I will start with an assumption that this is the case. If we face any contradiction in between, we will understand with proper logic and explanation that our assumption was wrong, and then we will correct ourselves and go ahead. Why I am telling you all this is that I want you at the end of this course to be able to analyze any DC-DC converter, any unknown DC-DC converter in this approach. This approach never fails. There can be multiple inductors. Simply do KVL, draw the inductor voltage waveform, apply this volt second theorem. You should be able to find out the relation between all the voltage ports in the circuit. Only thing is, make sure that the way the current paths that you are taking, the voltage polarities that you are taking are all logical. If you are facing some contradicting or wrong things in between, that means some of your assumptions were wrong. Correct them. That is the approach of solving unknown DC-DC converters. Okay, so
Sir,
this
if there
is
are
clear.
multiple inductors,
There are cases. Oh, there are cases.
uh, sir, in that case, applying the volt second balance in any one of the inductor will give the V naught by V.
That depends. That depends
Uh,
on the circuit complexity, how many variables you have.
okay. The It depends on the voltage appearing across the inductor.
Hmm. How many variables you have in the circuit, how complicated they are. Okay. Any more question here? We'll go to the next question then. Okay, this question is interesting. I will put this circuit here and make it large. Although it's large enough. In this DC-DC converter, the switch Q is switched with a frequency of 10 kilohertz and with a duty ratio of 0.6. All the components in the circuit are ideal. The initial current through the inductor is 0 ampere. Energy stored in the inductor in millijoule at the end of 10 complete switching cycles is how much? We have to find out. So you see what is happening. There is a switch. Okay, I am turning this on, turning this off. So when I am turning this on, what is happening? We will draw the waveform. Will you remember? Okay, I will copy it. Here it is. Okay. Now I will first draw the switching waveform Q. So switch Q is on for say 60%. Okay, so it is on for longer, off for shorter duration, like this. Okay, I will draw the inductor voltage waveform and inductor current waveform, like this. So all the components are ideal here. So when you are turning off this turning on this switch, when you are closing this switch, again we will take some positive direction of voltage and some positive direction of current IL. Now when Q is closed, the current path is this source is supplying the inductor, so the voltage is 50 volt. 50 volt. And when this is open, so the current was flowing in this direction, it will current was flowing in this direction, so it will keep flowing like this. Current will keep flowing like this, but the voltage that will appear across the inductor is minus 50 volt, is minus 50 volt, like this, 50 volt. So this is how the circuit is being operated. 60% of the time inductor is getting 50 volt, 40% of the time inductor is getting minus 50 volt. Are you smelling something here already? Something is wrong. 60% of the time inductor is getting 50 volt, 60% of 40% of the time inductor is getting 50 volt. I am forcing that.
Yeah, that volt second balance is not
Volt second balance is not uh,
it is not happening. So the current through the inductor will continuously rise.
yes, so it's not that the voltage
Saturation.
volt second balance is not being applied, it is being applied, but it is valid, but it cannot be applied here. Why? Because the circuit, if you keep operating like this, will never reach steady state.
Yes. Okay.
So it started from zero, say it increased this much. When it reduces, it is reducing across the same voltage. Ideally it would require more voltage,
That
but
too less
across the
time.
same voltage reducing, so I am not reaching zero. So next time, whatever delta I had here, I will have the same delta I, so it will be even more. So the current will keep increasing like this. So this circuit will never operate at steady state if you keep the duty ratio at 60%. Now let us solve the question first. We have been asked to find out the energy stored in the inductor in millijoule at the end of 10 complete cycles. So basically what we have here is an average voltage of, so if you find out VL, average VL over a complete switching cycle, that is how much? That is 0.6 times 50 minus 0.4 times 50, right? So 0.2 times 50, 10 volt, right? It's 10 volt. So we can say that these many things are not happening, only these many things are not happening, only a 10 volt source is connected. Since we have been asked to find out the energy at the end of one complete switching cycle, our job is made easier. So we can simply say this much. This is the circuit. This is the circuit. So what is V? V equals L di dt. So 10 equals, what is the inductance value? 10 millihenry. 10 millihenry. 10 into 10 to the power minus 3 times delta I by delta t. Delta t is the total 10 cycles. So 10 kilohertz. So 10 into 1 by this. So can you do this? How much should it be? So this 10 gets cancelled out, this 10 gets cancelled out, this 10 to the power 3 comes here, so this also gets cancelled out. So all I have is delta I equals 1 ampere. So at the end of 10th cycle, say I draw a breakage here. At the end of 10th cycle, my current is here. My current is somewhere here, so this will be 1 ampere. Instead of doing this, you can do it step by step also. For the on time, how long, I mean how much is the current, this exact current value we can find out. For the off time, how much it drops, another current value you can find out. So this much is the increment in one cycle, multiply it with 10, you will get how it is at the end of the 10th cycle. You can do it that way also.
Okay,
So
so
what
now
is
here it will be some 0.1 amps.
1 ampere?
No, this first cycle
First
differential
cycle
might
is
be
zero point
point.
0.1 amps, 0.1 amps, and the 10th cycle it will be 1 amps. So the question is energy stored in the inductor in millijoule at the end of 10 complete switching cycle. So energy E is half Li squared, so half 10 millihenry into 1 squared, so this is basically 5 millijoule.
So there is a chance that it might have got saturated.
Yes, it will get saturated.
Uh, Sir, if it gets saturated also, can we say the energy is stored in that?
Yes,
Not
energy
only
is
in the
stored
linear region.
because when it is saturated, your L value is small but I value is very large. So energy is always stored.
This energy equation applicable even though L is varying, sir.
Even though L is varying, yes, this is the instantaneous energy stored in the inductor. At any moment, if the current flowing through the inductor is I, then the energy stored in it is half Li squared. Now in this circuit, if you see, if I keep D equals, or I should say D less or equals 0.5, since this is 50 volt, this is also 50 volt. So if I keep D less or equals 0.5, then the circuit will always operate at steady state. So if the D is below zero point 0.5, what will happen is, say this is D, so it will operate in discontinuous conduction mode. It will come like, go like this, drop, stay at 0, again increase like this, drop, stay at 0. In this fashion it will operate for D less than 0.5. If you keep D at 0.5, it will operate at CCM DCM boundary. Then the current will look like this, increase, decrease, like this it will keep on operating at CCM DCM boundary. Beyond 0.5 it will become unstable. uh, it will, the current will keep rising, it will, and the inductor will go towards saturation gradually. Clear? Interesting problem, right? So I can give you this circuit with some other voltage values, maybe say 100 volt here, 200 volt here, and ask you what is the maximum duty ratio that you can safely apply to this circuit. Okay. What is happening? This is a first order system whose transfer function is given by k by s plus a. Okay. And its response to unit step input are shown in the figure. This one. Find the value of k. So this k we have to find out. Right. So they are saying that it is a step function. So you see the input rt, if I write in Laplace domain, is 1 by s, right? A Laplace transform of a step function. So the output in Laplace domain will be 1 by s times s plus a. Now they have asked us to find the value of k. See, we already know from this figure that it is approaching 2. Can I not apply infinite value theorem? Infinite value theorem says the value at infinity is this.
Yes.
Sorry, is k. So it comes out to be mm, k by s plus a. K by am I doing something wrong?
It's k by s. Mm,
I was thinking k will be equal to 2. So what we get is k by a is 2. So k equals to. Is it correct? I am thinking something is wrong here.
Sir, do we need to find the coefficients by partial?
Uh, what coefficient are you talking about?
Partial fraction. Sorry, what is that? That we will write a by s plus b by s plus a.
No, why is it required? This have I written this thing correctly? Just a minute, give me a second. I have to take this call. Okay. So what we are discussing here is this problem. Yeah. So did I write the infinite value theorem correctly?
So the c of t comes out to be k by a into 1 minus e to the power minus at.
Yes. Laplace transform. No. Inverse
Yes.
Laplace. No.
Yes, sir.
What is it? C of t
Equal to k by a into 1 minus e to the
minus t
power
by a,
minus.
something like this. It should come.
Yes, sir. K by a into 1 minus e to the power minus t. At. K by a into 1 minus e to the power minus at.
Okay. 1 minus. Yes. So if t tends to infinity, it becomes minus infinity. 0 is k by a. So t tends to infinity. Ct becomes k by a. Right.
Mm,
So it is correct.
yes,
So if it is approaching 2 here, Okay, so k equals 2, that is one thing. I think we have another information also, which is this. See, they have given the initial slope.
Yes, sir.
Initial slope they have given. So if I do initial slope means c
Yeah, dc of t by dt.
dct of dt. Just a minute. I will take some more space here. So dct of dt, that will give me k by a. 1 becomes 0, minus a comes out, so it becomes a e to the power minus 80. So k e to the power minus 80. So c prime t at t equals 0 is k,
Yes, sir. K.
right?
Yes,
So
sir.
they have given, right, k. Okay, so what is the initial slope? Initial slope is, they are saying 2
2 by
by
point
0.2, which comes out to be 10. Have I done it correctly? Y by x, 2 by zero point 0.2, time is in seconds, so it should be directly zero point 0.2. So k is 10
Yes, sir.
and a is 5.
Yes, 5.
Say t, differentiation is correct. K by a, 1 is 0, it will minus becomes a, it will minus a t, k it will minus a t, t tends to 0 because it is 1. So k is 2 by 0 0.2, it is 10. Yes, k is 10. Okay, straightforward question, just control related. Only thing is that I missed out that there is one more information is here. All right, this question is a bit interesting. In the circuit shown below, the diodes are ideal, inductance is small, and output current is non-zero. And the direction of the output current, what they have given here, it must be positive also, right? Current source cannot be open circuited, so it must be positive. Now, which one of the following statements is true? So the test statements are all about how long D1 and D2 conduct. Okay, we'll see. So this is an AC source. So I will draw the voltage. Okay. Now the diodes D1 and D2, they are in common cathode configuration, right? Common cathode configuration. So at any instant, we have to find out. So if I take this as the ground, then we have to find out what is the potential of A. Say I write A1. So if the potential at A1 is positive, then D1 is conducting, otherwise D2 is conducting. Clear till now? Okay.
Yes, yes, sir.
So this is Vs. Now there is something between Vs and L1, which is A1, which is L, inductance, right? Suppose at any instant, say not any instant, say at this point t equals 0, if D2 was conducting, let us say D2 was conducting, so it was short circuiting the current source, so the voltage of Vk was 0. Now as soon as Vs starts increasing, what will happen is inductor is getting a positive voltage, and so it starts conducting. No, gets if the inductor has to conduct, D1 must turn on. So when will it turn on? Hmm, will it turn on somewhere? Let us see. Okay, so at t equals 0, or we can say at t tends to 0 plus, means just when the voltage has crossed positive, at that moment inductor was not conducting. If we take like that, we have to justify all our assumption later. So if I take like that, then what is happening is, hmm, then inductor acts like a short circuit, right? V equals L di dt, no current, so inductor acts as a short circuit. So whatever the source voltage is, that much is VA1. So D1 starts conducting. So if D1 starts conducting, D2 must stop conducting. But is it possible that this much current, say it is a positive current, that suddenly shifts from D2 to D1? It will not. But it will shift slowly. So I believe there will be a time when D1 and D2 will remain, both will conduct, and that means these points will be virtually short circuited, will be at same potential. That is due to commutation. So if we look at the currents at D1 and D2, it will be like D1 was something like this, it will drop to 0, and ID2 and D1 at a current like this, that will rise. This was I0. After that, ID2 will become 0, and ID1, it will keep conducting like this.
Sir,
Hmm.
sir, is actually when the voltage source is of the polarity that you have written,
Hmm.
then D1 will conduct, D2 will be reverse biased. When the potential reverses of the source reverses, then D2 will be conducting and D1 will be reverse biased.
See, the thing is, there is an inductor also here. So there is a VL, which is L di dt.
Yeah.
So the source voltage is not the anode voltage of this diode. We have to consider this L di dt also. Anode voltage
Sir, I
is,
think when the inductor will charge only in the first day, it will never discharge it.
no, it will discharge, but it will keep conducting, it looks like, or for some time at least it will conduct. Say if it comes like this, now the voltage is reducing. No, the current will keep increasing until here, because the voltage is positive throughout. So it will increase till here. Just a minute. Not draw such a large slope. At least here it looks like. Then it reduces. And when it is reducing, in this fashion, L dIdt is negative, but VA1 is still positive. Again, there is a constant current. Constant current does not have any effect on the inductor voltage, but we are not able to get back to this initial state. Hmm. So data current increases. And when the current reaches somewhere here, ID2 will again increase, maybe something like this. But duration, we cannot comment about duration here, right? I can see that D1 will conduct more than 180 degree, but what about D2? Can we say anything about it?
D2 passes through current sources. Through flowing through D2 along this current source. This
Okay, I
path.
think I got this. See, uh, I can write V on this, right? Vs minus L di dt. Now, say if I call this theta equals pi, now what happens is when theta is between pi and 2 pi, what is happening is Vs is negative and L di dt is also negative, right? The current is dropping. So, mm, at some point beyond theta, maybe somewhere here, VA1 will become negative. Not at theta equals pi, but after somewhere after theta equals pi. VA1 becomes negative. So when it becomes negative, the current commutation starts once again. So it is not here. Because now the diode D1 must turn on. So somewhere here it looks should be like this. It should be like this. They have said the inductance is small. This must be having some implication here. What happens when inductance is small? Inductance is small means current increases first and decreases first.
Sir, without diodes, shall we analyze and then if we put in diodes, it will be.
Without diodes, you want to analyze first.
Yes, sir. I'm just saying. Over, we
See,
can.
thing is that without diodes, if you talk about, means are you short circuiting the diodes? You want to short circuit the diodes? In that case, the circuit becomes quite straightforward. This source is always short circuiting through here, and here whatever we get, that much we are getting. They have not talked about initial condition also. Since there is no dissipative element here, the initial condition also matters.
Uh, since L is very low, shall we consider I to be zero? Is that initial current I2 to be zero? Because it will
Which
dissipate
current?
fast. Since L is very
Hmm.
low,
Hmm.
the current through the inductor, can it be assumed to be zero because it will dissipate faster?
That we started like that only, no? That ID1 was zero initially. Then when the voltage is positive, the current starts increasing. And what is happening is there is a commutation between D2 and D1. That is the current. D2 was carrying the full I naught. So that commutes to this. Because around this zone, D1 must be conducting alone. Both of them cannot conduct because Vs is positive.
We need L value here to comment on this.
Let me try to answer this in this fashion. Let us see if we can do this in this way. Suppose there is no inductor at first, okay?
Okay.
For the time being, let us say there is no inductor. Let me not draw the diode also initially. Okay, just look at this, what I am thinking, like this. Okay, what is it? This is a rectifier. Okay, half wave rectifier, right? Now I am saying that the load of the half wave rectifier is heavily inductive, or in other words I can say that the load current is essentially constant. I discussed this in one class, that in that case we can replace it with a current source. True.
Yes,
Now
sir.
in this case, when it is positive, when the input voltage is positive in its positive half cycle, then it's fine, it is supplying the load. But when it's negative half cycle, then this diode D1 is cut off, so you must give a path for the current to flow. You cannot open circuit a current source, or you cannot open circuit an RL load that first, right? So to do that I include this D2. Now if I draw IS, source current, this was my VS. Wait, if I draw IS, how is it? When the source voltage is positive, then only D1 is conducting. So it is like this. And when the source voltage is negative, source current is 0. This is IS. So IS is nothing but ID1, and if you consider ID2, it is like this. True. So
Yes,
this is the case if we do not have the inductor. Now we are considering a more practical source. What is a more practical source? That has a small, in this small inductor term gave me the hint. So this is LS, this is my IS. Okay, now what is happening is, look at this position. So as of now, forget the inductance for a time being. Okay, as of now, diode D1 was conducting for 180 degree, diode D2 was conducting for 180 degree, when, if there is no source inductance. Now there is a source inductance. So what is happening is, look here, look here, this phase is the commutation phase, right? This is where commutation is happening. The current is shifting from D1 to D2. This is also another commutation period. Current is shifting, let me draw it with red. Current is shifting from
Sir,
D2 to D1,
sir,
another commutation phase. Just a minute, let me complete.
okay,
I will take your question.
okay.
So these two are the commutation periods. Now let us take this commutation period CP1, let us say commutation period 1, where the current is being shifted from D1 to D2. So D1 had some current, say say 10 ampere, whatever, I not, this current that suddenly shifted to D2. Now that was possible when the inductor was not there. Now we have an inductor in the path. So this sharp drop in current is no longer possible. Current cannot suddenly shift to D2. Similarly, if you talk about commutation period 2, when the current is shifting from D2 to D1, again current cannot suddenly go from D2 to D1. The D1 current here cannot suddenly have this jump to the positive. So the problem that comes with the presence of this inductor is that with these portions here and here, it cannot drop this first here, it cannot rise this first here, so it must have a transient. So basically, if I have the source voltage like this, if I have ID1 like this, initially my ID1 was how what? It was coming like this and dropping down like this. And my ID2 was what? Coming like this, rising like this. Now, one more thing you can write from here is that by KCL, ID1 plus ID2 equals I naught. So this must always be satisfied. Along with that, we know that they cannot change very fast. So now what will happen? ID1 will come like this, then drop slowly. ID2 will come like this, then rise slowly, such that their summation is always I naught. Okay, I am exaggerating this commutation periods, they are not that large. Like this, again it will rise slowly, it will drop slowly. So this much was 180 degree. Now this much extra commutation time gamma has been introduced, gamma. So both D1 and D2 will conduct for more than 180 degree. Is it clear? I will take Shanti's question. Just before that, tell me, is it clear?
Yes, sir.
Sir, turning on is having a delay, no? So,
See, it's not about the turn on delay I am talking about. Okay, the devices are
no,
ideal.
yes, ideal. Because of this inductance, the
Yes,
current switching to the one device is taking some time. Maybe can be considered as a gamma. Then how come 180 plus gamma can be given? It's only 180 now.
yes. So 180 plus gamma is the total time that the devices are conducting for.
Okay, okay. So my question is,
Hmm.
during positive half cycle, D1 conducts. You mean to say D1 is conducting?
Hmm.
Will this current source will not force D2 to conduct?
During positive half cycle, no, current source will not force D2 to conduct, because you see, between D1 and D2 who will conduct, that depends on the potential. So if I consider this as ground, then the potential of this point, if I write VA, these two diodes are in common cathode configuration. So whoever anode has higher voltage will
That
conduct.
okay.
Sir, how to find this gamma?
How to find this gamma? That would okay. Let us see
Sir,
if we can.
explain this negative half cycle, sir. Negative half cycle. How D2 is conducting? Explain that. D1 is reverse biased. How D2 is
Okay,
conducting?
so it was going like this. Now the voltage is suddenly negative. Okay, at this
It's
point the voltage is
negative.
negative.
Okay.
So what is happening? This current was constant. Okay, let us again go back in this case where there was no inductor. So what happened here? The negative voltage reverse biased D1,
Yes, D1 is open now.
reverse biased. So here also, when it is like this, the voltage is negative, and so okay, let me write the equation. So say I am writing the voltage equation at this point. If I write, so at this point D1 was conducting and D2 was off. So VA was Vs minus Ls di dt, right?
Yes.
And
Yes.
this current source current is a constant, right? So this
Yes.
is anyway zero. So
Yes,
whatever my
sir.
supply voltage, that much is the anode voltage. So if the supply voltage becomes negative, anode voltage becomes negative,
Okay.
right? So the anode voltage is negative. Anode voltage negative means what? Now D2 has higher anode potential. So the current must shift from D1 to D2.
Sir,
Oh,
basically,
okay. Then who is supplying energy to D2, sir? Then I not.
I not, yes.
Current. Yeah, that's what I'm asking. Oh.
Hmm. Rakesh, not Rakesh, sorry. Raja, you are saying something basically.
Sir,
Sir,
sir, actually this
Just a
I
minute.
naught,
Yeah. Go ahead.
this I naught is I naught basically in this circuit.
Hmm.
The current I naught is commutating between D1 and D2 based on the polarity of the voltage source.
Yes. And the inductor is introducing a delay. A question just came how to calculate delta this gamma. Let me see how many questions we have. Okay, let me see if we can quickly find it out. How to find gamma. So gamma, so what is happening? You see, during this commutation period, CP if I write, both D1 and D2 are conducting. Everyone okay with that?
yes.
So during this period, I can write or I can draw the circuit like this. Like this. So this current is ID1, this current is ID2, sorry, this I naught. What we have is this ID1 plus ID2 equals I naught, and this is Vs, and we can write Vs equals L ddt of I d1. Now Vs, see I am doing it here, okay, we are looking at the negative half cycle, so I can write, since we have shifted our origin to here, I can write Vs equals minus some V sine omega t, okay. So what we have is minus V sine omega t equals L ddt of this. So this dt, if I write, then L di d1. If I integrate it, now you see how long is this situation occurring. This situation is occurring for gamma, period. Since I have written gamma in angle, so omega t is gamma, so t is gamma by omega. So 0 to gamma. Okay, let me make it easier. Instead of dt here, tell me if you do not understand. I am writing omega t, taking one omega here, such that I can write this equation integration 0 to gamma. And 0 to gamma, what is happening to id1? id1 is changing from its full value of I naught to 0, right? Yes. So what I can write is this becomes sine theta d theta, so cos theta minus v by omega, cos 0 is 1 minus cos gamma, that comes out to be L times id1 0 to this, so minus I naught. So this minus cancels out. What I have is 1 minus cos gamma is equal to L I naught omega by V. So cos gamma is 1 minus omega L by V I naught. Calculations are correct?
Sir, yes, sir. But how do you initially select VSC minus V sin omega t?
See, what we are doing is we are trying to find out the gamma period, okay, gamma time.
Okay.
So we can take this part, we can take this part. Although I said I am doing it here anyway. Say I am doing my calculation here during this zone, right?
Okay.
During this zone, I am doing my calculation.
Okay.
This is also gamma. Now,
Mm.
during this time, what is happening? This voltage is negative. So what I am doing is I am drawing my waveforms from here. You see here. So this is the time when my ID1 drops like this and ID2 comes out like this. So I am doing all my calculations here in this zone. So here is the Vs. That's why I wrote it minus V sin omega t. If you have the waveform like this, would you not like write minus sin omega t?
Mm.
Sir,
Yeah.
if L is 0,
Yes, I was going to say that.
then gamma should be 0.
So if L is 0, then cos gamma is 1. So gamma is 0.
0, yes. If L is infinite, then gamma should be 90 degree.
If L is infinite, 1 minute. No. Yes. Gamma 90 degree means what? Cos 90 is 0. L infinite means it will not even
Cos.
conduct. Gamma 90 degree means what? Means cos gamma is 0, no? So L will be somewhere Vi naught by omega.
Yes.
Sorry. V by I naught omega. Now one more interesting discussion we can have here. Let us see. So in this time, say when the inductor was not there, if you look in this case, what was the load voltage? The load voltage was simply this, right? So the load voltage was, if you do 1 by 2 pi V by 2 pi sine theta d theta 0 to pi, so V by pi cos theta cos 0 1 minus 1 2 2 2, yeah, V by pi load voltage. Now what is the load voltage? Let us see. See what is happening. Let me draw it once again. I'll draw it over this. Okay, now we have a conduction, we have a commutation zone here. Here there is a commutation, here there is a commutation. Previously what would happen, sorry, I will draw it with some other color. What would happen, the load voltage used to be, say I'm drawing from here, used to be 0 until here, then it would start following the source voltage. Now since the commutation is going on, if you see commutation is going on means it is this condition, this circuit condition here, this circuit condition means the load is still short circuited, means the load voltage is not increasing here. Here also it is still 0. From somewhere here it is exactly following the source voltage. So I am losing some output voltage, that is clear. I am losing some output voltage. So what is my output voltage right now? So if you look, say here, say I am taking my origin here. So 0 to gamma, there is no voltage at the output. So now my output voltage, if I write say VDC, it is 1 by pi, 2 pi. It starts from gamma, goes till pi, sine theta d theta v. So it becomes V by 2 pi cos gamma minus cos pi, so plus 1. This is my output voltage. Now if you look here, just a minute, did I do something wrong? Okay, so cos gamma plus 1. So look at this equation. We have already derived cos gamma. So cos gamma plus 1 is 2 minus this thing. So V by 2 pi 2 minus omega L by V I naught, right? Cos gamma plus 1 2 minus omega L. So it is V by pi minus dimensions. I have to check the dimension once. Omega L by 2 pi I naught. Omega L is resistance. Resistance times current is voltage. Yes, dimensions are matching. So this. So if I have a source inductance here, so what now? Let us look back from very beginning. So initially what we had an ideal source with ideal diodes supplying a heavily inductive load whose current can be practically considered constant, like this. In this case, we had this output voltage V DC as V by pi. Now, when we are considering this source inductance, the output voltage becomes V by pi minus this. So definitely there is a loss in output voltage. Now, one interesting thing, if you look here, you see it is I naught times something, which has, I will write it here, which has dimension of resistance. So effect of source inductance is as if it is not here, rather there is an extra resistance here whose value is given by R equals omega L by 2 pi. So I naught current is flowing, which is causing a drop of this much, such that my output voltage is reduced by this much. I naught times this resistance. Clear?
This it should not be considered as R. R is a lossy component. It is only drop. So we can consider it a impedance.
Yes, it is not considered as R. I am just saying
Reactance,
that
we can
it looks like as if a resistance has been connected there,
say. Yeah,
which is
reactance
causing
we
this
can
drop.
say.
Hmm.
X value.
Since this is directly proportional to I naught,
Yes, sir.
so as if a resistance has been connected, which is causing this drop. But yes, there is no loss. So I think
Sir,
yeah,
if position of D1 and inductor is interchanged, then what we have seen will not hold for that circuit. Position
Position of
inductor and
diode and inductor you
D1
want.
and D1 and inductor is changed.
In that case, we cannot call it a source inductance anymore.
Oh,
But anyway,
inductance.
yes, because source inductance is not available to you. No, the behavior does not change.
Behavior will be same.
Hmm.
Since inductance is small, because of that,
Yes.
Sir,
Yeah.
sir, why we went for this VDC here? We have derived this thing. Can you repeat this again?
I am just trying to find out what is the effect of source inductance on the output voltage. See, our
Okay.
original question was very simple. How long with D1 and D2 will contact? That we have found much before. Only by drawing these waveforms we found that both will conduct for more than 180 degrees.
180, yeah.
Now, I said that it is 180 plus gamma. Now a question came, how much is gamma? Can we calculate it? Calculate that.
Yeah,
So
you
we can
calculate.
calculate how much is gamma. So how long the commutation period would be, that depends on the load current, depends on the frequency of the voltage, depends on the voltage and the inductance, literally everything in the circuit. Now I showed you that during the commutation period, basically what is happening, we are short circuiting the source. You see what I said, this is a source inductance. So
Yeah,
this whole thing is your source,
yeah, yeah, please.
right? So if you
Yes,
want to see source voltage using an oscilloscope, you will connect a probe here and here. This point is not accessible to you, right?
yes, it will show 0.
Now
Yeah,
since we are short circuiting the source and load periodically in every cycle, we saw that there is a loss in output voltage during this period. When the commutation is going on, output voltage is still 0. Then we tried to find out how much is the loss. So we found out the average voltage when there is no source inductance and when there is source inductance, and we saw that this much is the reduction in output voltage. Okay.
yes, sir.
All right, we will, sorry, go ahead. We have many more questions. This is easy. If not, if today is not possible, I will see how long I have taken the class for today. Since just a minute, it's been 1 hour 53 minutes. Okay. Okay. So we have some more time now. We can, at least from late, and we can work. Right. So what should be the value? So this is a closed loop converter, closed loop control of a buck converter. Can you identify the buck converter? Voltage.
Yes, sir.
This is a buck converter.
Yeah.
Now, what should be the value of D for fast and robust control of output to regulate a voltage reference of 12 volt in the below flow? So this thing is there in the lecture. If you look here, this is the extra thing that is connected to have a fast control. Thing is, we can avoid this. The Have you seen this lecture?
No, sir. About to see.
So if this is error, if this is the PI controller, whatever control voltage I am getting, that I can directly control, that I can directly compare with a sawtooth and give it to the gate of the switch, like this. This is possible. This also gives you a closed loop control of the converter. But the thing is, if you look here, say in this case itself, you have input voltage 20 volt, output voltage 12 volts, so you have a duty ratio of 0.6, So it is 0.6. So at steady state, what will happen is, so if you have 0 to 1, then this Vc will come out to be somewhere close to 0.6 volt, close to 0.6 volt. Now you see, whatever block I drew here, what I drew here is red ink, is actually a very generic block. Any circuit where the output voltage increases with D, we can apply this controller directly. Only thing is that we have to tune the PI, KP and KI values. But without much knowledge of the controller, only with one knowledge that with increasing D, output voltage increases, we can directly apply this control circuit. This control circuit is not using any knowledge of the power circuit. So what is happening is we are giving some voltage reference, say 12 volt voltage reference we are giving, and the circuit starts from this Vc here, it starts from 0, and since it is a buck, and if you now connect a buck converter, it will maybe in some whatever, if you have PI, then it might show you a response like this, whatever, it will settle at a value of 0.6. So it starts from 0 and goes to 0.6, quite long time it takes. Now the logic here is, with this circuit given in the question, is that we have knowledge of the power circuit, that it is a buck converter. Why not use the power circuit? Why not use the knowledge? So how to use the knowledge? So what is the knowledge? The knowledge is that my output voltage versus D is a straight line, given that input voltage is constant. And if I need output voltage of 12, my D will stay somewhere close to 0.6. So why not give a D equals 0.6 here itself? So I am already sending the PI output, not PI output, the output here at this point to here to 0.6. Now you see, at steady state previously the PI output was 0.6. It has to vary from 0 to 0.6. But now in this case, in this new case, my PI output at steady state will be 0. And for perturbations in the power circuit, for perturbations in the load, it will have oscillation around 0. So what I am doing, so what I am gaining by connecting this extra block here is that I am manually pushing the control circuit very close to the steady state value. I know where the steady state is by my knowledge of power circuit. So the controller ultimately handles the rest of the non-idealities or whatever, and we can reach the steady state very quickly. So this is the logic behind this, logic behind adding this extra block here. So the answer to the question, what should be the value of D, is 0.6. Okay. All right, we'll go to next question. Slope compensation is there in the lecture. It's very interesting thing. If you have not gone through it, go through it. A very, very interesting thing. But thing is, if you have not already gone through the slope compensator compensation lecture, I don't know whether solution to this question will make any sense. The boost converter is used to charge a battery in a current controlled manner. The boost converter is being supplied by 36 volt PV source. So a 36 volt PV source, boost converter, and it is charging a battery VB, and the battery voltage is 60 volt. Uses a MOSFET power semiconductor switch which is switched at 50 kilohertz. The boost converter uses this much inductor, maximum current of 33 ampere. Slope in the current reference is expressed in volts per mH. The slope is nothing but the slope of the falling current zone. So whatever slope you have, so we have V equals L di dt, right? So they have asked volts per millihenry, so V by L is di by dt. So that is during the falling. So whatever the slope of the inductor current during the falling current zone, that is the slope of the current reference. The current reference looks like this. I'm sorry. How does it look? Yeah, it looks like this. So the slope is same as the slope of the current in falling zone. So V by L. So what is the voltage across the inductor when the current is falling? Voltage across the inductor is 36 minus 60. If I take a mod, then 60 minus 36 volt per millihenry they are asking. So 4. So sorry, 24 by 4. No, slope is negative. Let us take the actual one. They have not asked for mod. So 36 minus 60 gives minus 6 volt per millihenry. This is the answer. Now why it is so, you have to watch the lecture. It's actually a very long thing, long story. There is a long story in the sense step by step it is derived. First the regular current control, then what is its problem, then how that problem is mitigated by this slope compensation. There is a whole lecture.
Sir, are we making the inductor current to follow this slope here?
Kind
Because
of,
falling,
yes. Actually, if there is any large perturbation, it might so happen that the inductor current is rising like this. So if you keep a current reference like this, it will rise beyond requirement and it may not be able to stabilize. So if you keep a slope compensation like this, it will stop here and within a cycle it will stabilize. That is the logic behind it. Okay. So this is the last question we will discuss today. Inverter we will leave for next day, okay? In the below figure, the asymptotic body of a PI controller is plotted. What is the value of omega 2 in radian per second? PI controller. So PI controller, how does it look like? PI controller is Kp plus Ki by S. So Skp plus Ki by S, if I write, then if I take Kp outside, it becomes Kp S plus Ki by Kp by S. So asymptotic Bode plot, you have to divide it into two parts. One is this S, 1 by S. 1 by S will cause a drop in minus 20 decibel per decade. And here it is a 0, S plus Ki by Kp. So this will provide a slope of plus 20 decibel per decade. You all know what a decade means?
10 times the frequency.
10 times. So 1 radian per second to 10 radian per second, it's a decade. All right. So what will happen is initially it will start with a minus 20 decibel per decade. It will reach somewhere at Ki by Kp. Where this 20 decibel per decade will also come into picture. So the minus 20 plus 20 will cancel out each other and it will be like this. So basically what they are saying here is that straight line that is dropping has a slope of minus 20 decibel per decade. Right. Now you see a total drop of 50 decibel is there. 30 decibel to minus 20. So 50 decibel drop is there. So how many decades are there? So how many decades? So total, if it is 20 decibel per decade, then 50 by 20 totals 2.5
2.5
decades are there. So from here to here, it is 2.5 decades. So if it is 1 decade, we multiply by 10. If it is 2 decades, multiply by 10 squared. So if it is 2.5 decade, then omega 2 should be 0.1 times 10 to the power 2.5. Can you tell me how much it is? Somewhere close to 31, 32.
Yeah, 31.6 radians per second.
31.6 radian per second. Right, is it clear? We are already over time today. This is a questionnaire inverter that I will discuss next day, and if possible I will also show you what is modulation index and what is the relation between output voltage and modulation index for SPWM. Okay, then that's all for today. We'll call it a day. We will meet next week once again at 7, no, not 7, 6 p.m. as usual. Thank you.